Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at more topical past paper questions for Cambridge A-Level Physics, this time on the topic of Astronomy and Cosmology. And these are questions 5 to 8, and you'll find this document in the description down below. So I've taken questions from the more recent exam seasons, 2023 and 2022, and I've put them together especially in the topics of medical physics and astronomy, because they are more recent topics, more recent additions to the syllabus, and so it's more difficult to find, especially astronomy questions, if you go further back in the years. And so you can use this document, you can use these questions as practice, and then use these videos if you need help answering these kinds of questions. And so in the previous video, I did questions 1 to 4, and in this video, I'll do the remainder of the questions 5 to 8. And I think there's enough here content-wise to at least cover all the content. Although the questions will look different in your final exam, which is coming soon, they will at least be based on the same content. So the problem-solving skills might differ slightly, but the ideas will remain the same. And so we start with question 5, which, again, the subject code for A-Level Physics, Cambridge A-Level Physics is 9702. This is from the winter exam of 2022, that's October-November 2022. It's question paper 4, variant 2, and it's question number 9 from that paper. We are told that figure 9.1 shows the visible part of the emission spectrum from hydrogen gas in a lab on the Earth, and the numbers indicate the wavelength in nanometers represented by each line. So I have hydrogen gas in the lab, I observe its emission spectrum using a diffraction grating, and I see some of the lines that appear here. These are the wavelengths of those lines. They could be different colors, red, green, blue, whatever. We want to explain how the emission spectrum provides evidence for the existence of discrete energy levels for the electron in a hydrogen atom. So we have to use the emission spectrum that we're given and show how, or explain how this emission spectrum proves that they are discrete energy levels. So very importantly there, we have to talk about the discrete energy levels for the electron in a hydrogen atom. So we're obviously going to have to talk about the light itself at some point, and obviously the light is going to be related to the electron energy levels, and so we have to make the connection. So what we know is that the energy of the emitted photons, which is the lines of light that we see in the emission spectrum, it would be nice if it was in color, but you get the idea. The energy of those corresponds to their wavelength, corresponds to their frequency, whatever you want to say. And these photons are released when an electron changes energy level. And so if the wavelengths are discrete, as we can see 1, 2, 3, 4 very discrete bands, that means the electron energy level change must be discrete as well, which obviously means that the energy levels themselves are discrete. And so, again, I can say this completely. I think words are enough for us to say this. And we can say that the energy of the emitted photons, I'm going to be omitting a few words here. The energy of the emitted photons corresponds to the wavelength or the frequency of those photons. As we know, E is equal to HF, corresponds to its wavelength. I'm using wavelength because wavelengths are shown in the emission spectrum. And the photons that give off these lines, these specific lines, is released whenever an electron undergoes a change in energy level. I can simply say when an electron changes energy level. Or when an electron changes its energy, when there's a change in electron energy. So what this means is that the discrete energy changes, and hence the discrete wavelengths that we see. The discrete wavelengths, I should say that first, the discrete wavelengths imply discrete energy changes, which can only happen if there are discrete energy levels. And so I can say, and hence discrete energy levels. And so that's the emission spectrum in general. This doesn't have anything to do with astronomy and cosmology. This is just about the emission spectrum on its own. So it's a little bit of quantum physics in here. So the energy of the emitted photons corresponds to its wavelength, and this photon is released when an electron changes energy level. Since they are discrete wavelengths, we must have discrete energy changes, and hence discrete energy levels. So that's how the line spectrum for specific gas proves that an atom has a discrete energy levels. And it happens for all atoms and hence all elements. Part 2 says that figure 9.2 shows 5 of the energy levels in the hydrogen atom. The wavelengths of radiation shown in figure 9.1 relate to the transitions to the minus 3.4 electron volt level in figure 9.2. So here we have an energy level diagram. We have different levels in this diagram, and the lowermost, or the ground state energy, would be minus 3.4 electron volts. And every transition from a higher level to the lowest level, minus 3.4 electron volts, gives off a photon with one of these wavelengths. So that's what they're telling us. The transitions there are what give rise to the wavelengths of the photons in that emission spectrum. And we want to show that the energy level X, the unmarked one, is minus 1.51 electron volts. So how do we figure out what that energy level, what the value of that energy level is going to be? What we know that if I jump from EX to the ground state, or I can just call it E naught, the lowest state, which is minus 3.4 electron volts, what this must be equal to is the energy of the photon that's released, hc over lambda. But how do I know what photon is going to be released? Well, it's going to be, if I look at all of these levels, and if I look for the wavelength that's going to correspond to the biggest jump is going to give me the highest energy, and so the highest frequency. But I want the lowest frequency and highest wavelength. The highest wavelength being 658 nanometers, which must correspond to the lowest jump. And the smallest jump is going to be going from X to the ground state, as every other jump is going to be too big. And it's going to give me high frequency, high energy, and a not very high wavelength. So I'm going to only look for the smallest jump to give me the highest wavelength. And so EX minus E naught can be rearranged, and I can find the energy of level X, which is minus 3.4, keep my values as negative, plus the value of H is 6.63 times 10 to the minus 34 times C, which is 3 times 10 to the power 8, divided by the wavelength 658 times 10 to the minus 9. We are lucky that we are told exactly what the final answer should be, because if you calculate this, you do not get the final answer, because I'm taking a value in electron volts and I'm trying to add it to a value in joules, which is not going to work. So I must convert this second term to electron volts, so I divide it by 1.6 times 10 to the minus 19. So I get a value in electron volts. So now I can add electron volts to electron volts, and what I get is minus 1.51 electron volts. And so I had to figure out, okay, what is the highest wavelength? The highest wavelength is 658 nanometers. It's going to be the smallest jump, which is the jump from X to the ground state, which is what I want. And so obviously I'm going to have a high value of lambda because I have a low value of frequency. And that's how I can confirm. Obviously I know it should be from X to the ground state because I was told that, but I have to look that this corresponds to the highest wavelength. So that was a 3-mark question. If they didn't tell us to show what the energy level value was, it'd probably be a 4-mark question, one for the accuracy in the final answer. Part B says the same part of the emission spectrum from hydrogen as in A observed in light from stars in a distant galaxy is shown in figure 9.3. The numbers indicate the wavelengths in nanometers. So what I notice is that the emission spectrum from hydrogen, from stars that are using hydrogen to undergo fusion, the emission spectrum looks identical, almost identical to the hydrogen in the lab, but everything is shifted. Everything appears more red. It's all shifted to the right in this case. And every wavelength, every line has a higher wavelength. And this is because we know that the star is moving away from us, so the light must be redshifted. The spectrum shows the same pattern as figure 9.1, but with different wavelengths, as I just said. We first want to state the name of the phenomenon that gives rise to the change in wavelengths. We know this is the Doppler redshift, or simply the redshift is fine. So that's because the star is moving away from us, its light has been stretched out and hence has a higher wavelength and is redshifted. What does this phenomenon show about the motion of the galaxy? It shows that the galaxy is moving away from the observer. So it is moving away from the observer, or from us, or from Earth, or whatever, or from our galaxy, if you would. And anywhere you look in the universe, you'd find the same thing. We're then told to use one of the lines in figure 9.1 and the corresponding line in 9.3 to determine the speed of the galaxy relative to the observer. Remember, when we want to find the speed of something relative to an observer, we need to use the redshift equation because we know that thing is moving relative to the observer. The redshift equation says the speed of recession v divided by the speed of light c is the difference in wavelength for that specific line, delta lambda, divided by the correct wavelength, or the wavelength that is emitted by that star. And so v over c is 429 minus 411. You can use any of these lines. I've decided to use the first one on the left, the lowest wavelength, 429 minus 411. And then divided by the wavelength of this line in the lab, in our reference frame, 411. And therefore I have to find v, so I can multiply this thing by c. And so v is equal to 18 divided by 411 multiplied by c3 times 10 to the power 8 meters per second. And so I get a speed of 1.31 times 10 to the power 7 meters per second. To two significant figures, this is 1.3 times 10 to the power 7 meters per second. And so that means it's a significant speed at which this galaxy, and hence the star, is receding from Earth, if Earth is the observer. We're told then that the galaxy in B is known to be at a distance of 5.7 times 10 to the 24 meters from Earth, significant distance. And we want to use our answer in B3 to determine a value for the Hubble constant. This is, if you remember the equation, straightforward. The speed of recession is equal to Hubble's constant h0 times the separation of the two objects d, which means that Hubble's constant h0 is equal to the speed v divided by the distance d. So I'm going to use 1.31 times 10 to the power 7 divided by 5.7 times 10 to the power 24. And what I get is a value 2.298 times 10 to the minus 18 per second. And so this to two significant figures will be 2.3 times 10 to the minus 18 per second, or 2.3 times 10 to the minus 18 meters per second per meter, which conceptually makes Hubble's constant easier to understand. So that was a fairly long question, a very long question actually. But it was a good question because it sort of brought together a lot of different concepts, especially the quantum physics of the emission spectra and the cosmology of it all. So how can we use the emission spectra, the line spectra, to actually determine how far away a galaxy is? So this is a good question. I would suggest attempting this question on your own before using any mark scheme or guide, as I would for any question, but this one specifically was quite interesting. So that was 13 marks altogether. The next question is number 6. It is from the summer exam 2022, that's May-June 2022. Question paper 4, variant 1, and question number 10 from that paper. And we are asked to state Wien's displacement law. Now, in my previous video, we've done this a few times. Wien's displacement law says that the wavelength of the maximum intensity of radiation is proportional to the thermodynamic temperature of that body. Okay, so the wavelength of the maximum intensity, or the intensity that is that has the greatest rate of emission, which is basically the same thing. Intensity of radiation by a body, you can say, is inversely proportional to the body's thermodynamic temperature, or absolute temperature is also fine. Temperature measured in Kelvin. So that's Wien's displacement law in words. You can also write the equation and explain each of the symbols, whichever is more comfortable for you. Wavelength of the maximum intensity of radiation is inversely proportional to the thermodynamic temperature, which sort of means that the next question is going to ask us to use Wien's law to calculate something. And here we have a figure 10.1, that's showing the wavelength distributions of electromagnetic radiation emitted by two stars A and B. So I have the rate of emission, the intensity on the y-axis, and the wavelength on the x-axis. So all stars emit radiation across a band of wavelengths, across a spectrum of wavelengths, but some wavelengths are more prominent than others, and that's where the peak is. And that's how we can tell what color the star appears to be. If most of the wavelengths are blue, then the star appears blue, so the peak is blue. If most of the wavelengths are red, then the star appears red, as most of the light we see from the star makes it look red. So that's what we're going to use this graph for. We're told that the surface temperature of star A is known to be 5,800 Kelvin, and we want to determine the surface temperature of star B. Now you always need a temperature that is known, and you need to find the wavelength of, you also need to know its peak wavelength in order to find the surface temperature of another star using Wien's displacement law. So we said there's an inverse proportionality. We did say there was an inverse proportionality, so we need to apply it here. Lambda B over lambda A, the ratio of peak wavelengths, or wavelengths at which we get the peak intensity, is the inverse ratio of temperatures, TA divided by TB. And we want the temperature of star B, so if I rearrange and do some mathematics, I get TB to be, it's going to be TA times lambda A over lambda B. Now what is lambda A? Well, it is the wavelength at which I get the peak intensity for star A. Peak intensity, and that wavelength is 0.5. I'm going to ignore the micrometers because it's a ratio, those micrometers will cancel out. Divided by the peak wavelength for A, or rather for B, is somewhere around here, and with the ruler and careful examination you'll find this value to be 0.65 micrometers. And then we multiply this by the temperature of A, 5,800, and hence using Wien's law we get this surface temperature to be 4.462 multiplied by 10 to the power 3 Kelvin. So to stick with the convention of writing the temperature in the thousands, we write this as 4,500 Kelvin with two significant figures. And so the surface temperature of star B is 4,500 Kelvin, and that's why you can see that the peak of the peak wavelength for star B is shifted to the right. Higher wavelength obviously means lower frequency and lower energy. Sort of makes sense. Lower energy means lower surface temperature. So you can kind of keep that in mind, that your temperature should be lower. If your temperature is higher, you've obviously inverted a ratio somewhere. And so that was 2 marks. We are told that star B then appears less bright than star A when viewed from the Earth, and we want to use figure 10.1 to suggest with a reason how else the physical appearance of star B compares with that of star A. So less bright, but less bright is only one reason. I need to find another thing that would differ in physical appearance for B as it would for A. So if I look at this, I've already actually explained it. The peak wavelengths are different for star A and B. We even wrote them down, they're different numbers. So how does that tell us what the physical appearance will be for the two stars? So which one has a bigger peak wavelength? So let's first write that down. So the peak wavelength, we know that the peak wavelength for B is higher, 0.65 as compared to 0.5. So I'm going to say the peak wavelength for B is greater, or star B is greater. And so if it has a higher wavelength, it is more towards the red end of the spectrum. So in a simple way, we can say it simply looks redder. It's more red than star A. So if star A was a yellow star, star B would be orange. If star A were a green star, star B could look yellow or orange or red or whatever it may be. So the peak wavelength is greater for B, and so it looks more red than star A. Question C says the lines in 10.1, figure 10.1 have been corrected for redshift, and they ask us to state what is meant by redshift. So we've done this enough times already. You know what this is. Redshift is when the observed wavelength of an object, I can simply say the observed wavelength appears more red than the wavelength emitted by the source. So the source gives out blue light, but by the time it gets to us, it's stretched out so much that it appears more yellow or green rather than blue. So it's been red shifted. The observed wavelength appears greater than the wavelength emitted by the source. The last question wants us to explain how cosmologists are able to determine that light from a distant star has undergone redshift. So how do we do this? Well, what we do is we look at the spectrum of light from the star, we examine that, and we compare it to the known spectrum of the gas that we are getting from the star. So the primary element of the star, usually hydrogen. I can take hydrogen in the lab, look at its spectrum, and I get a few lines. If I look at the hydrogen gas is coming from a star, that emission spectrum looks the same in shape, but is shifted towards the right, which tells me that, yes, there's hydrogen at the star and there's hydrogen in the lab, but something is happening to the light in the movement from the star to us, and it's being pulled outward because it's moving, the galaxy is moving away. So how can I say this in words? I'll say the spectrum, and I'm sticking to the mark scheme here because the wording is very specific, but you can also go in and write a much more long-winded answer. The spectrum of light from the star can be examined and then compared to the known spectrum of its primary elements, which I say is sometimes hydrogen, but also helium and other gases as well. So the spectrum of light from the star can be examined and compared to the known spectrum of the primary elements. And then we can tell that there's been some redshift if all the lines are shifted to the right, or to the red end of the spectrum rather. So overall, that was a good few conceptual questions toward the end and a 9-mark question, but you can see that these astronomy and cosmology questions are important and you should pay very careful attention to this topic. 9 and 13 marks are significant in your overall scheme of paper 4. The next question is number 7. This comes from the summer exam of 2022. It's question paper 4, variant 2, and it's question 9 from that paper. And we're first asked to state Hubble's law. A1 says state Hubble's law. And I think we've done this before many times. The speed of recession, I like using the word recession because it helps me, prevents me from saying the speed at which a galaxy recedes or moves away. Simpler to say recession. Speed of recession of a galaxy from an observer, it can be any observer, is proportional to the distance of that galaxy from the observer, or the distance between the galaxy and the observer would both mean the same thing. The speed of recession of a galaxy from an observer is proportional to the distance of the galaxy from the observer. And so that's Hubble's law in words. You can also, again, write the equation and explain the symbols. We're then told to explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine that the universe is expanding. So it kind of builds onto the last question of the last sub-question of the previous question. Well, what we do is we observe the wavelengths. The spectra are the important things. So the wavelengths, or the wavelengths in the observed spectra, are greater than the known values and what we would measure in the lab, and this means that the light has been redshifted, been stretched out, and so galaxies must be moving away. Redshift happens when things move away from you, as we know from the Doppler effect. So the wavelengths in observed spectra are greater than their known values, their lab values, or their whatever. And this means the light has been red-shifted, or has undergone redshift, you can say. And we can conclude that the galaxies that we are looking at are moving away. All galaxies are moving away. Everywhere we look, we see this. For any galaxy, that means we are not egocentric, and that again means that everywhere we would be to observe this, we would notice the same thing, that everything is moving away from each other, so the universe must be expanding. The wavelengths in observed spectra are greater than their known values. This means that light has been redshifted and the galaxies are moving away. Expansion of the universe. Lastly, we want to explain how Hubble's law and the idea of the expanding universe lead to the Big Bang theory of the origin of the universe. Okay, so the Big Bang theory basically says that the universe started at a single condensed point where all matter existed. Okay, so all objects in the universe are moving away from each other, and we can see this because wherever we observe from and wherever we look out to, what we see is things move away from other things, right? And objects at greater distance recede faster. So the further you are away, the faster you are moving. And what this means that if we bring all of these objects to a point where the distance is zero, then they wouldn't be moving apart from each other at any speed, right? The speed of recession would be zero, and the speed of recession is only zero when the distance is zero. V is equal to h naught d. No recession if no distance. So there must be some point in space that was initially where all the matter was condensed before some big bang happened to push everything apart. So again, how do I say this in words? So I can say that all objects in the universe, most important point is all objects in the universe are moving away from each other. Again, it's not just us that are special and everything moving away from us, but everything is moving away from each other. And what we know is that objects at a greater distance are moving faster. Greater distance, I can also say recede faster. And so what this means is that all matter must have been close together or densely packed or at one point in space at some time. Together at some point, specifically at some point in the past. I should say at some point in the past, which is the Big Bang theory. All the matter was condensed into a singularity or a single point, and then the Big Bang happened, which spread this matter out throughout the universe. So all objects in the universe are moving away from each other. Objects at a greater distance recede faster, and all matter must therefore have been close together at some point in the past. So this question was completely theoretical, which means you really needed to understand your things like Hubble's law, the expansion of the universe, emission spectra, how they tell us that the universe is expanding because of redshift, and so on. So again, that was 7 marks, but again, 7 marks is still a significant amount for a question. Now, the last question I'll do in this video is question 8, and this comes from the March 2022 exam, question paper 4, variant 2, and it's question 12 from that paper. So you see these questions usually come late on in the exam paper. We are asked to state what is meant by the luminosity of a star. So the luminosity of a star is the total power emitted by the star, but specifically the total power of radiation, not by any other sources. So total power of radiation emitted by the star. So only the energy of all of the radiation being emitted by the star every second, the total power of the radiation emitted by the star. That's its luminosity. We're then told that the luminosity of the sun is 3.83 times 10 to the 26 watts. The distance between the Earth and the sun is 1.501 times 10 to the 11 meters. We want to calculate the radiant flux intensity of the sun at the Earth, giving a unit with our answer. So we know that flux intensity F is luminosity L divided by 4 pi times the distance between the two objects, d squared. So the luminosity is given, 3 significant figures, 3.83 times 10 to the power 26 divided by 4 pi multiplied by the distance between the Earth and the Sun, 1.51 times 10 to the power 11 meters squared. And this is going to give me 1.337 times 10 to the power 3 watts per square meter. So to three significant figures, this will be 1.34 times 10 to the power 3, or you can say 1,340. And unit of measurement for radiant flux intensity is watts per square meter. Remember, you're dividing a watt by a meter square, since 4 and pi don't have any units. We're then told to use the data from B to calculate the mass that is converted into energy every second in the sun. Okay, so remember that a watt, I'm just going to put a little note here, which you could do in pencil if you would like, that a watt is equivalent to a joule per second. So that power is 1,340 joules every second spread over every meter. Okay, so every square meter rather. And so I want to know how much of mass is converted into energy every second in the sun. And so E is equal to mc squared if I find the energy mass equivalent. So the m is coming from the mass of the hydrogen atoms that are being fused together to form the helium and releasing the energy, which means that if I wanted the mass, it must be the energy per unit time, which is 1 second, divided by c squared. But we already know that the energy per second is the power. And so it's total energy. Rather, in this case, we want the total energy. So it's 3.83 times 10 to the power 26. That's the amount of joules per second that the sun is emitting, divided by c squared, which is 3 times 10 to the power 8 squared. So we're using the total amount of energy that the sun is converting, not specifically per square meter. And so we should get a total mass of 4.256 times 10 to the power 9 kilograms of matter. So the three significant figures, this is 4.26 times 10 to the power 9 kg. It's 4.3-ish billion kilograms of hydrogen being used up by the sun every second. That's a lot of hydrogen. If you wanted to recreate the energy that the sun is providing, you'd need 4.3 billion kgs of hydrogen. So quite a significant amount. D says the radius of the sun is 6.96 times 10 to the 8 meters. And we want to show that the temperature of the surface of the sun is 5,770 Kelvin. Now, immediately when I'm given the size of something and I want to find the temperature, or vice versa, I'm given the temperature and I want to find the size, I know that I must apply the Stefan-Boltzmann law. Luminosity is equal to 4 pi sigma, or the Stefan-Boltzmann constant, times the size of the radius of the star squared, times its temperature raised to the power 4, which means its temperature is, so I know that many of your calculators will not have the fourth root symbol, so you're going to have to use all to the power 1 over 4. The fourth root of L divided by 4 pi sigma r squared. Okay, like you know, I prefer to do the algebra first and then the arithmetic. So if I put my values in, this is the fourth root of 3.83 times 10 to the power 26 divided by, which is L, the luminosity, so divided by 4 pi. Now the Stefan-Boltzmann constant you'll find in your data sheet, it's 5.67 times 10 to the minus 8 in standard units, and this is multiplied by the radius of the sun squared, 6.96 times 10 to the power 8 meters squared. And if you put this into a calculator, you find that this is, as they asked of us, 5,770 Kelvin. So you didn't need every step of the way that like I did it, but I'm doing this to ensure that I don't make a mistake in rearranging the equation. And I'm showing the values that I'm using when I'm calculating my value for the for the temperature. And so you do get 5,770 Kelvin, which is the surface temperature of the sun, which is a 1-mark question, but was a little bit of working. The final question I'm going to do is 8, E, and it says here that the wavelength lambda max of light for which the maximum rate of emission occurs from the sun is 5 times 10 to the minus 7 meters, and the temperature of the surface of the star Sirius is 9,940 Kelvin. Okay, and we want to use this information from D to determine the wavelength of light for which the maximum rate of emission occurs from Sirius. And so Sirius has a much higher temperature than the sun. It is a much bluer star. So you'd expect the wavelength to be much smaller than 5 times 10 to the minus 7. And we know from Wien's displacement law that the peak wavelength, the wavelength of peak emission, is inversely proportional to the temperature, the surface temperature of the star. That means we can then again use ratios, that the peak wavelength for the sun divided by the peak wavelength for Sirius is the inverse ratio for temperature. So it's the surface temperature of the star Sirius divided by the surface temperature of the sun, which means that the wavelength at which maximum rate of emission occurs, I can just put my values in now, is 5 times 10 to the minus 7 multiplied by the surface temperature of the sun, 5,770 Kelvin, divided by 9,940 Kelvin. And so the wavelength here I find to be 2.902 times 10 to the minus 7 meters. So to keep to the convention of 3 significant figures, this will be 2.90 times 10 to the minus 7 meters, 290 nanometers, which I can see is a lot less than that of the sun, which corresponds to the fact that Sirius is a hotter star and hence it's more energetic. So the radiation that we receive from Sirius should be more energetic, and the answer for the wavelength sort of confirms that. So another interesting question, there were many variants of questions that we looked at, and there are possibly more if you go back maybe to 2021, 2020, and so on. But I think the concepts were all covered fairly well in these questions. So if you found this video helpful, please leave a like, leave a comment, and subscribe to the channel if you haven't already. From me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.